In this video, we'll focus on talking about various kinds of C program data types that we can use in our programs, and what are their equivalent assembly construct that would do the same thing. So one thing I want to emphasize is that when a compiler takes a C code and tries to convert that to assembly language, as much as possible they will use indirect addressing to access variables and read, write to memory locations. And the reason for that is with indirect addressing you can have the base set anywhere as long as the relative distance is kept the same. The code can be relocated anywhere in the memory. And if you're interested, you can go to basically the www.engrcs.com and under the look at the text that accompanies these videos to see how a assembler, how a compiler will assemble it. Or better yet, MPLAB has both the C compiler and the assembler, so just write a code with that data type in it and see how it converts. And it's quite constructive to do that, because you will see from a human point of view it's a little hard to understand, but because they're using indirect addressing and taking advantage of post-increment, pre-increment, plus W and all of that, they are able to start from a location, use what they need, and then when they do a return from a function they can give it all back. So that's pretty handy. But anyway, in this video, as I'm talking about the types, I'm going to stick to not assume we have an absolute address and not necessarily use indirect addressing. But again, there is a place you can go to get that information if you're interested. Our objective here is to understand what the data types are and how they get translated to memory locations. Great. So let's start with the first one, and the first data type and the simplest data type we come across is called a constant. And in a sense, what we are trying to do is say, let's say I have a define, and I will have a number, some base, usually capitalized. Capital letter is used to refer to these. So I can say pound in C. I can say pound define base, and I can say base is 130. We do that because 100 base is a lot easier to remember than 130. And if I use this base in many part of my code, or this variable in many part of my code, this allows me to go change it here, and everywhere in the code it gets changed. Now so the question is, how would you, if this is the C construct, what is the PIC microassembly construct? As you already know, you can use exactly the same thing. You can say define base 130, or you have an alternative. You can say base equal EQU equal 130. That does the same thing. And the other thing is, the other thing is you don't have to just use number. You can use strings and text and all of that in here. Now, constants, do they take up any memory? The answer is no, they don't take up any memory. All they are is basically a name for something you want to insert everywhere in the code before it assembles or compiles or any kind of work is done to it. So it doesn't take any memory space at all for a constant. The next simplest construct is called a character. And character is basically an 8-bit unsigned value. Pretty universally, that's what it is in C. And so when I declare a character, CHAR, let's say a character example. Okay, and I say, okay, now go ahead and set this character example to H. Okay, in C, if this is the code in C, what is happening in assembly? In assembly, or in assembly, what you're doing, you're basically saying, okay, go ahead and have so you got to reserve a location, and so you say define CHEX since our memory data memory location starts, I'll give it starts at 80. I'll give it the first byte to that, and I only have to allocate 1 byte because character is 1 byte. And all I'm doing is that at some point I'm putting the ASCII equivalent of H into this location. So if I recall correctly, the ASCII equivalent of hex is 060 hex 68 hex. So I'm basically so what I'm doing in assembly, I'm doing that define, then I'm doing a move LW0x68, and I'm just moving that moving that 68 into the location CHEX, which the way we defined it is basically 80. So what happened? What happened when this code runs in the data memory? Look, if this is the data memory, the location 80 now has a 68 hex in it, and that's all that happened. So that is a character. So the next thing we learn typically is that we're gonna do a integer. Oh, actually, yeah, that's fine. Let's go ahead and go to the integer. And integers in C, I may declare an int example, and let's just do it, so put a value in it so we can kind of have an experience of creating that as well. Now we know that on C language, depending on the machine it runs on, the int is going to have different sizes. Since we are running on a 16-bit machine, our int is going to be 16-bit or 2 bytes. If you have a 32-bit machine, then your int is going to be 32-bit. If you have a 64-bit machine, then your int is 64-bit. So depending on what machine you run, your size of your int changes. That's a good thing to remember if you ever program at level where you need to know the size of the maximum number you need to calculate. Okay, so now if I say int x is equal to, I don't know, something big like or maybe small. Just this way I don't have to figure out. So 128, that's easy. And I'm putting a decimal 128 in here. Actually, let's make it hex, so it's easier to break it up. So if I do a hex 128 and put it in int x, what's going to happen? Well, first thing is, just like I did define, in this case, when I'm doing the assembly equivalent of this thing, I have to do define int x low, because I'm going to have 2 bytes, so I've got to have a low, so I got to reserve a location for low, and then I got to come back and do another define or equal, both are good enough, define int x high and another location. Okay, now and then of course I have to do 2 of these things. I've got to say move LW0x28, that's the low byte, and I got to move that to move WF. I got to move that to so not CH, int example low, and then I've got to come back and do the high portion of this move LW0x1, that's the high byte, and I got to move that to int example high. Okay, so that's what happened. So what happened in the memory? In the memory now, because of this instruction, now we got location 8.1 has got 28 in it, and 8.2, the next byte, has got 0x1 in it. Okay. All right. So that's integer. I forgot to. So you sometimes you also have a string, and we're going to talk about arrays. Strings are basically a character array where the last character is a null character. So that's all a string is. Okay. Okay. So we've talked about integer. What is next? Well, the next one is how about if you have a real number? In that case, in C you have a float, and in earlier we talked about float as we called this one was the single precision floating point, which means this is going to be what? This is going to be 4 bytes long. And if you don't remember that, you might want to go look at the video which shows you how you take a real number and convert it to a full float. So it's going to be 4 bytes. So if I do a float, for example, float FL example, and declare that, in assembly language I have to do 4 locations. So in assembly language I have to do define, and I have to have 4 location because that's what's going to generate. So for example, if I start, this is going to be 0x83, 84, 85, and 80x86. So I'm going to have that spread from here to here. And again, it's simply what we had studied earlier. You're going to have 4 bytes. Those 4 bytes going to be from the least significant to most significant. Okay. How about double? Double, theoretically, double will be double precision floating point. So if I have a double example, supposedly in most typical machines I should have 8 bytes, because that's what it requires for the double precision floating point to be put there. But the little secret is that in PIC Micro, whoever wrote the compiler, they felt it did not make sense to do a double. When C compilers were written for PIC Micro, the compiler writer decided that, you know, for this system, double just doesn't make sense. So what it does is if you declare in C a variable double or single, both of them become a single. Double or float, both of them become single precision floating point. Okay, in larger processor, a more capable processor, they would be different. One would be 8 bytes, one would be 4 bytes. Okay. And then the next item is, we probably should talk about pointers at some point. And when you do like a let's say you say, I don't know, you say I have a character pointer, and that's how you declare it, and then do you have another character value in assembly and in the machine code where actually this is being created. What happens is that the character pointer is just the location of the memory, so it doesn't really take any room. The only thing that takes room is what this character value has, and character pointer is just pointing someplace. So this doesn't take any room in memory, but this does, okay? Because this is just a pointer, 0x8, 0 or whatever, to a location. This is the one that actually takes space. Okay. Just a little quickie on pointers. All right, the next thing is an array. An array is pretty straightforward, right? So you can have any type of array. Let's say you have an integer, and let's say um, example array, being very creative here. And then you put a number in here, and that tells you, let's say 10. That basically tells you I'm going to have a character 0, and I'm going to have character 2, character 3, character 4, character 5, character 6, up to 9. So for example, if this one says, okay, let's go ahead and, excuse me, let's go ahead and it says that, let's go ahead and put, this is a little C program which says, I would like you, oops, that's an integer. Okay, let's not start with an integer. Let's start with a character. It's a little simpler. And just because it's 1 byte, integer would be 2 bytes. So we can do one next as an integer, but let's start with the character, get the sense of that. And so if I've got this thing, and then someone comes and say, okay, character 9 is equal to J. And let's say we come here, and in C is going to allocate it based on how much, where the memory is starting to become available, and it's going to go down 10 bytes. If you're writing in assembly language, you have to do all of that. So you basically have to say, okay, I'm going to define the name of the array, and that's the same thing in C. The name of the array is pointing to the very first element. So the name of the array points at XAR 0. Okay, so let's, if we start this one, we restart everything. So let's say we started it here. That basically means that I'm going to have a memory scheme where my array starts at 0x80, and I'm going to count 10 when I get to 0x89. That's where my last character resides. Okay, since it's saying put J in 9, is wanting to put J right here, and I just happen to know that the ASCII character for J, or hopefully I'm right, is 6A. So we'll put that in here. So that's more or less what it is. If you want to do it here, it's going to be move LW 0x6A and move. Now here would be really cool to use, like put 9 in W register, and then do an LSFSR, and then move WF 2 plus W, and that way you don't have to sit down and do the calculation of where I should be putting it in. But since we've done the calculation, we'll just do it that way. So move WF 0x89. Now if I were to come back here and write this thing as integer, EX AR210, how much room do I need for this case? Okay, in this case I need 20 spaces because each integer is 2 bytes. So I'm going to have 20. So if, let's say, somebody comes and say, go ahead and put in location, I don't know why I'm stuck on characters. So example AR2, let's say in location 2 you want to put 0x9215. Okay. Now since this is an integer, each one is going to have a 2 byte. So when I go over here, I have to do 2 move LW and AF. And what's going to happen in the memory, if I start my array, let's say start it at 0x80 again, this array, what's going to happen, my end of my array is going to be at 20. So my next location, as I was saying, it's going to be at 20 locations later, which in hex would be 0x93. So these 2 bytes gonna be EX AR29. These 2 would be the 0, and then one would be next to him, two of them. And then finally down here we're going to have the EXAR2 2. So that's going to go in here, and what's going to happen, 15 hex is going to go here, the first location, which is going to be 1 2 3 0x84 and 0x85. So 1 5 and 9 2. Okay, so that's going to be how the arrays work. The last item is structures, and I know most of you are familiar with structures. Structure is a way of, throwing different things in there. Let's take a look at a structure and try to see if we can figure out where in the memory things will reside and what they would look like. Let's take an example and deal with it. So let's say someone writes a C code and asks us to give him a location in memory where things would happen. So let's say if a C structure that is built is struct, and struct is gonna have, it has a character array, it's a string of names basically, is name, and that is got 30 characters. So names can have up to, well, actually we're gonna fix it to 30 characters. Each character takes a byte, so we're gonna basically use the 30 bytes there, and then we're gonna have an int, and this int is gonna be the student ID, and then so since this is a teaching thing, we're gonna have another character, and that's a grade for the grade, and that's 2. There's room for 2 grades for every student. There could be 10 or whatever, but let's leave it at that. Each grade can be up to 255 since you only got 1 character in it, and we're gonna call this struct students, and we have 20 students in our class. So basically what we're doing, we are creating a struct that has 30 characters plus an integer, which is 2 bytes, plus 2 character for grades, which is 2 bytes. So each one of those structs actually are 34 bytes large. Okay, so let's say someone says, okay, this is great, and you're gonna start building this thing in memory, and let's say we are using pick micro, so our start of the memory is going to be located as 0x80, and that's going to be our first byte in the memory, and they are telling us, tell me where in the memory location of struct, the structure students, too many, students 2, this is 20, I will have 20 students here, 2 dot grade 1. So they're asking us where in the memory is this location of this in the memory. So we know that this starts here. We know each construct is going to take 34 bytes, and I have to go through student 0, students 0, then I have another 34 byte, which is going to be students 1. Then I come to students 2. So students, so the start, this is going to be students 2. So before I get here, I've got two full structure of students, and the way I know it's 34 is because name needs 30, integer needs 2, character needs 2, total of 34. So the big challenge is now, where is the beginning of student structure 2? And what I'm going to do, I have to add 34 and 34 together, and then come up with the hex value, add it to 84, and that will tell me where I am. Okay, so when I add 34 and 34, that's 68, and then I convert it to hex, add it to 80 hex, which puts me at 0. So this location is started, this thing is going to be 0xC4. Okay, so great. So I have the beginning of this, but they want grade. They want the second grade, not grade 0, grade 1. They don't want grade 0, they want grade 1, which means I have to figure out how much room does the name needs. The name needs 30. Then I need to figure out what the integer needs. The integer needs 2. And then the first grade will take 1. And then I'm finally at here. Okay, so I have 33. I gotta convert 33, which is 21 hex, to this thing before I know where this location is. So this location is going to be sitting right here. So this location is going to be basically C4. Actually, let's use a red. So this is the location that we're asking for. Is going to be C4 plus the decimal 33, which puts us at E is a hex E5, hopefully. Yep. Okay. So that's something we need to do, and sometimes we have to do that. We look at a code is supposed to do something, but not the right data is getting into the memory, and we need to figure out where all the memory resides and where the variable ends up, so we can go check to see how it's doing. So this is an example of you looking at a C code, figuring out when the code runs, where in the memory different things will happen. And one thing to be cautious is very common, is that remember that C, when we write an array, this first element is setting at location 0, and then increments from that. So when we say we've got 20 students, we actually have students 0 through student 19. That brings us to a kind of end of an overview. So what were we trying to do? We were trying, in this particular example, we were trying to go through the various data types. I'm sure there are more data types, but these are some of the most common ones. Constant, we talked about that. The big thing, the unique thing there is that doesn't take up any memory space. We talked about a character, it takes up 8 bits, 1 byte. Integer picks up 2 bytes, 16 bits. Float, although in float officially and formally, based on the standards, a float should be the single precision taking 4 bytes, and double should be double precision taking 8 bytes room. But for pick micro, just remember they just decided that single precision was plenty, and both for double and float they use single precision. Then we talked a little bit about the fact that the pointer is just pointing to something. It's not a memory location. Only the variable itself takes up room. As far as the array is concerned, the big thing to remember is when you say you've got an array of 10 items, you're actually, when you count it, it's going to be 0 to 9. It's still 10, but it starts at 0. And just remember that whatever type you use, whether it's a character, integer, float, or structure, it's basically, if you say I've got 10 of these things, you got to make room for 10 of whatever size each element is going to be. If it's float, it's going to be 4 bytes. If it's a structure, depending on how big your structure is and what's in it. And then if it's an integer, then it's going to be 2 bytes per. Okay. And then we did this little exercise of a struct and being able to locate where the struct ends up, or a specific element of that struct ends up in memory, and this one we assumed we started at age 0, and we found out that if they're looking for third student, that would be the third student, because first student is 0, second student's 1, third student is 2, and they want to figure out what the second grade is, grade 1, and that puts us to location 0xe5 as where that piece of information is.